So welcome back. This file will show how to use the pseudo-inverse matrix to do a linear regression. So here in my file, I'm defining these two vectors, x1 and x2, as the encoded data I have, and I'm also added a vector of ones here with 28 entries as for x1 and x2. So I'm defining z as the matrix that, well, it adds x1, x2, and 1. And y here is the output vector. And as we've seen in the example here by the end of the slide, in this first example here, I'm assuming that the output is equal to x1 plus 4 x2 squared plus 5. So there is nonlinear relation, which I'll try to estimate using a linear regression. Okay, so I already know the form of the y. Okay, so these are the z I obtained. This is z, and this is the y I obtained here. Okay, so let's go on with the pseudo inversion. So I define z inverse as the inverse of my z matrix here. Basically, here I'm just trying to make it look a little bit better using the transpose of z. So once I obtain the z inverse, I will multiply it by the transpose of y. So I get the coefficients of my linear regression, which we called A in these slides. Okay, and this is the z pseudo inverse I obtained, and these are the c's or the coefficients I obtained, for instance. Now I'll compute the RMSE, which is the difference between the root of the mean square error. So I'll sum up, I'll iterate, and I'll sum up the errors here squared between yi and the y predicted I got when I multiplied c by z. Okay. Once I got this, I compute the root mean square error by putting this to the power 0.5. I mean the square root. So basically, this is the array of y's I obtained, and this is the root mean square error. And at the end, I'm plotting y and the y predicted. So the y here originally I got is the blue curve, and the orange one is the y predicted. And you see the two curves, they fit quite well. Okay, so I hope everything is clear. We'll continue with another example here.